In this video, we're going to look at calculating pH changes in the titration of a weak acid and a strong base. Our weak acid is acetic. Our strong base is sodium hydroxide. The axes aren't labeled on this graph. I don't know why, but this should be pH. And this is probably milliliters of sodium hydroxide. Whoopsie, and AOH. And AOH. That looks like a pretty typical graph. If I go like halfway in this big jump, I should be somewhere around the equivalence point. I would expect a pH something greater than 7, so somewhere around an 8 maybe. This looks like a typical graph for a strong base weak acid. Initially, we're going to calculate the pH of that acid, that weak acid. Acetic acid can be written in a couple different ways. You might be kind of familiar with it looking like this, hydrogen acetate, which is totally fine. This option is kind of like its, I don't know, structural formula. It looks kind of like this. First, there's a carbon surrounded by 3 hydrogens. There's another carbon. It's got a double bonded oxygen and a hydroxide group on the end. And when this thing dissociates, it's this last hydrogen on the hydroxide that goes into solution. Here, seeing it written as hydrogen acetate, it's a little bit more obvious how we dissociate that thing. But the other formula is totally fine too. That's maybe a little bit more structurally accurate. This is going to be a simple weak acid pH, which maybe you could even do without an ice table, or we could just do one for fun. So we'll have that acetic acid. I'll write it the way they've got it. The acetic acid, you could put water in, or you can leave water out. For an acid, it's not really going to affect your final answer. We're going to remove that last hydrogen, so we'll be left with the acetate ion, COO minus, which really is the same thing as C2H3O2. And then you could either put H3O plus, the hydronium ion, or if you left water out, you would just have hydrogen. Either way, same thing. We'll ice table this guy. Initially, we're 0.1000 molar. We're not going to care about the water, so maybe I'll leave that out. These ions are initially 0, so we know we're going forward. We don't know by how much, so we'll leave them as x's. This is going to be 0.1000 minus x. X and x. We just got to solve this thing for x, and we can calculate the pH. They give me the Ka, 1.8 times 10 to the negative 5th equals x squared over 0.1000 minus x. That K value is definitely small, so we can 5% rule this thing. We'll cross multiply, solve for x. Oh, I suppose I could leave a couple sig figs. We'll leave 4. The original molarity had 4, which is kind of random, but I can deal with it. How about 0.001342? And of these two x's, the one that I really care about is that hydrogen ion, or the hydronium ion. Now we can calculate the pH. Opposite log, 0.001342, hydrogen or hydronium. I'm looking at about 2.87, somewhere in there. 3-4 sig figs. It looks relatively accurate. If I just glance up at the graph, initially we're probably somewhere between 2 and 4. Seems about right. Okay, so that wasn't so bad. Just a typical weak acid. Now let's add the base. Okay, so just like the last titration, the strong acid, strong base, I need to recalculate these molarities. By changing the volume, we are changing the molarities. I like to do it right away so I don't forget. Initially, the acid, well, I think it was 0.1. We have 25 milliliters. That's a 0.0. I want to know the new molarity when I add 10 milliliters of base. So this final volume should be 35. M2. You know, these are going to be actually the same numbers as that last titration. They're the same numerical values as the strong acid, strong base, now that I think about it. This is 0.0714. We'll do the base. The base is 0.1063. Initially, we have 10 milliliters. We want to know the new molarity at 35. M2. Let's go 0.303. So numerically, these numbers might look familiar to you. They are the same ones from that last titration. We need to set up our ice table now. We're going to need to use the acetic acid in full because it will not dissociate by much. But with the sodium hydroxide, you can leave out sodium. That's a spectator. So it's just hydroxide that'll affect the pH in the end. I am putting this in as a double-sided arrow. I hope that doesn't drive you crazy. But this looks to me like it's going to be more of an equilibrium situation than hydrogen and hydroxide forming water. We've got hydroxide. He's got the tendency to attract hydrogen, so it'll rip off that last one. On the product side, we'll have the acetate ion, COO negative, and water. So we're going to ice table this with the molarities that we just calculated. The acid, the base, 0.0303. Initially, no products. So we're going to react this thing as completely as possible. We know that it needs to go forward. This is essentially a limiting reactant situation. The hydroxide is my limiting reactant. It's in a lesser quantity than that original acid. So we're going to bring it down to 0. And we'll react everybody else accordingly. This is going to go down to about 0.0411. These guys are both going up. And that's where we'll be at equilibrium. 0.3. We'll form a little water. 0.303. Okay, so now I assess the situation. In the last titration, all we had left was a little bit of excess hydrogen and water. So it was really easy to calculate the pH. Now I've got another ion in there. I've got that weak base, the acetate ion. So if I ignore water, because I really want to focus on the particles that will have the greatest effect on the pH, I've got some weak acid left over. And look at this. The acetate ion is the conjugate base, the weak base. Do these particles jump out at you? Are they slapping you in the face right now, screaming, buffer? We have a buffer. We've got water, which, who cares? Water's really not going to affect the pH. The two remaining particles in solution, a buffer. We've got the weak acid and the conjugate base. So this isn't really that bad. If I want to calculate the pH of this remaining buffer solution, we can just use the Henderson-Hasselbalch equation. pH is opposite log of the Ka value, which they gave me in the last question, plus the log of the charged particle over the neutral particle. So it'll be this 0.0303 over the 0.0411. Plug and chug. Throw it in your calculator. 4.61. Not bad. Look at what's remaining in the solution and calculate the pH accordingly. In the last problem with the strong acid, strong base, all we had was extra hydrogen and water. Now we've got some of that excess acidic particle, but we also form some of the conjugate base, which will affect the pH. So if you recognize that the remaining solution's a buffer, perfect. We can use Henderson-Hasselbalch. If I look at that graph, 4.61, and this was after 10 milliliters of base. That's probably about right. After 10 milliliters of base, if I follow this up and over, yeah, I am like a little bit over 4, like a little bit under 5 maybe. This region of the graph is called the buffer region. If you were to calculate the pH anywhere along this region, so anywhere from, well, not initially 0 milliliters of base, but as I add up to about like 20 milliliters of base, if you set up your ice table, you're going to have a buffer. So we call this the buffering region. It's at the beginning of a titration where we can add that strong base, but we don't see a giant increase in pH quite yet. That'll come when we get close to the equivalence point. So anywhere along that region of the graph, if I were adding like, I don't know, between 1 and about 20 milliliters of sodium hydroxide, you'd set up your ice table and you'd find that what's remaining in the solution is a buffer, and you can calculate the pH accordingly. After that, let's take a little break, and then I'll show you the last 2 calculations in this section.